Welcome to Building Cryptocurrencies with JavaScript. This course shows you how to design and code the fundamental concepts of blockchain technology to create your very own, very lightweight cryptocurrency by implementing the key aspects of successful crypto projects like Bitcoin, Litecoin, Dash, and others. We will progress through the videos of this course and build out a cryptocurrency project with a blockchain to provide accounting, proof of work to secure the blockchain, transaction validation to prevent double spends, wallets for creating transactions, and more. While any real-world crypto implementation is a work of art and can be considered a trophy in the Software Engineering Hall of Fame, thousands of man-hours were spent in creating every one that has emerged in this bold, disruptive new age of distributed computing. To better understand how all of these successful systems work, we will implement the most important components of each with JavaScript in our own home-rolled crypto project. Aloha, this is Brett Hooper with Aloha Codeworks in beautiful Maui, Hawaii. I'll be leading you through the material in this course. I'm a seasoned software engineer, technical evangelist, and longtime instructor. My career has spanned decades and has included clients from Fortune 100 companies, Silicon Valley startups, and the US military. I have produced many highly viewed technical trainings and am more than excited and grateful to bring this one to you. Thank you for your interest in this cryptocurrency course and in discovering from a high level how cryptocurrencies work and function in the wild. While the face of software engineering and development consistently changes over time, one of the most disruptive phases to present itself involves the distributed nature of blockchain technology and peer-to-peer architecture. While the networking behind these distributed applications is far beyond what we'll address in this course, the foundation of blockchain, which supports all cryptocurrency implementations, is what we'll embrace, design, and code. We'll create JavaScript classes that are capable of taking on transactions, organizing them in blocks, validating their contents, linking said blocks with classic blockchain strategy, and more. Using the familiar environment of JavaScript, we'll understand how the most important components of the blockchain and associated token transactions fit together and work together in a live implementation. This will prepare us for understanding code in real-world repos of the leading open-source cryptocurrency projects in the industry. While no blockchain programming experience is necessary as you begin with this course, having a high-level familiarity with blockchain, at least from a cryptocurrency perspective, will definitely help. It would be best if we are already aware of how blockchain systems provide data immutability and how the nodes in a blockchain network validate transactions, organize transactions into blocks, and broadcast ledger updates to all nodes to keep the blockchain fully distributed across the network. If some or all of these concepts are not real clear, a little Googling and reading can bring you up to speed quickly. Or you can just continue with the course and absorb these concepts as they're presented. Either way, you will have success in learning the material presented here and will emerge, by the end of this video series, a well-informed developer ready to approach code in a blockchain project that works with real-world use cases. In this course, as stated, we'll be programming in JavaScript, so a functional understanding and level of experience with JavaScript is best. We'll actually be working with Angular, so Angular experience will only make things easier. However, do not be afraid if you have not worked with Angular before, as every step will be explained fully and we'll walk you through action by action the things needed to be done to produce the necessary code for each component in the project we'll produce. So again, if you don't have any Angular experience, this course will be a double whammy. Each step of the Angular setup, config, coding, and execution will be explained fully with the assumption that students do not have any Angular knowledge, so everyone will succeed. Join me now as we take possibly the most significant step into the future of application development that we ever will. Blockchain and its associated technologies, architectures, theories, and implementations are impacting everyone and everything in the IT space and will continue to do so as we evolve into a significantly different world of information exchange, consumption, and development. This course gets our foot in the door now, which is when we all should be getting in, if we haven't already. Things around us are changing fast, and we need to be aware and functional with the concepts presented here. Let's go now to the next video and step through the items we'll learn and orchestrate in this video series to produce our own crypto system. With an understanding of why we need to learn about blockchain now and how it will affect software design across the board and impact what we do as developers in general, let's go through the concepts that we need to first become familiar with blockchain concepts. There are some basic but critical concepts that fit together to formulate the foundation of a blockchain system that we'll learn to work with directly. These are the following as arranged in a sequence of videos that compose this course's agenda. First, we'll have a discussion regarding blockchain technology in general and prepare ourselves for the more specific topics of study. We'll go from 10,000 feet and wind down to where we'll spec out the specifics of the basic components that will compose our own crypto system. Prior to working with these basic components, though, we'll need a development environment conducive to producing and running the code we'll write. So we'll get a new project with Node and Angular set up and running, ready for our first lines of crypto code. There's a specific environment approach that this course supports, which may be new to you, but you're sure to appreciate. With the environment all ready to roll, we'll get a new project set up for our crypto and blockchain code. Here we'll walk through the overall structure of the project as an Angular project and get an idea of the architecture and design of our crypto blockchain code structure and see how we'll scaffold the project and fill in the details. With our environment and project ready for code, our first development step will be in defining blockchain and block classes that will form the basis of our cryptocurrency machine. Here we'll get functions defined within a blockchain class that provide the blockchain's basic functionality, including block linking and block validation that will maintain the blockchain's integrity. As the blockchain class will be working with blocks, we'll also define a block class in which we'll define functions that will formulate the basic functionality of blocks within our project. These include the organization of transactions and transaction validation, as in, if Alice pays Bob, does Alice have the coins in her control in the first place? With our blockchain and block classes formulated, we can then introduce the concept of proof to our system. We'll bring in proof of work for maintaining validity in our system by keeping those who process transactions on our crypto network honest. We'll have miners invest their own resources into processing transactions and creating blocks so they're incented to be honest as they do so, and we can be certain that our system works as described, without worrying about miners taking advantage of any protocol. With the proof of work safeguard in place, we'll then define a mining protocol that will, in fact, incent honest miners and pay them out for processing transactions and mining blocks. This will also be the mechanism that creates our crypto coins and puts them into circulation among the members of the network. With a protocol and structure for mining in place, we'll add in another significant aspect of mining, which is validation of the blocks that this mining process produces. Each block that is produced by a miner will be presented to the blockchain for inclusion. Prior to blindly accepting that the transactions within the block are accurate and true, the block will be analyzed by different nodes of our network and will be either stamped with approval or rejected. The block will be noted with each approval and generally accepted after a certain number of validations. If a node finds an issue with the block, it will be rejected and will need to be remined by another honest miner. We'll write all of the code to flesh this protocol out. With a blockchain, blocks, a proof of work mechanism, and an implemented mining and validation protocol, we'll next create a wallet class that can be used as a mechanism for users to store and spend their coins. We'll use Angular's UI templates so coins can be received and spent from within the browser with a simple but functional UX. Then, to get wallets fully implemented, we'll stitch together our existing components to make transactions flow appropriately to and from the blockchain and the wallet concept we've created. With that, we'll have our functioning crypto system. Finally, we'll be able to add some code to simulate continued activity within our network where coins are being spent and received, and each transaction is processed into a block. Blocks are mined and validated, and our blockchain begins to grow, and more coins are mined into the system for users to trade. This will be the culmination of what we've produced, where we can see our crypto network take on a life of its own and flourish within itself. This is the plan. Let's now take the first step into the video series with a high-level look at blockchain technology. Join me in the next video where this discussion will start. We're now clear on what topics will be presented in the videos of this course and what we can expect to know after viewing them all. At this point, to help shape our mindset for the rest of the course, we will dive into our first topic: how do blockchains work? To begin understanding how blockchains function, we should be aware of what they do in the most generic sense. We describe data in the blockchain as a ledger, which is a good name. Another descriptive word for blockchain data is a register. The data is a list of events that have happened, a chronology, if you will. In cryptocurrency blockchains, these events are brief descriptions of monetary transactions. Alice paid Bill, Charlie paid Dolores, Bill paid Charlie. These events can also contain simple data chunks, like messages, documents, images, or whatever. This event data can be stored within a blockchain as a unit called a transaction, and not only represent a monetary exchange, as in cryptocurrency, but also just a nondescript event that places data into the blockchain for safekeeping. We understand now what makes up the content of a blockchain transaction. Let's talk more about how these transactions are recorded in the blockchain ledger. We know that a blockchain network is composed of a number of nodes. Each of the active nodes in the network do much of the same as one another, and that they all listen for new transactions to be introduced to the network. Say when Alice pays Bob, or Edward stores a selfie. Specific network protocol announces each new transaction to all active nodes of the network. Each node has its own copy of the ledger, and when a new transaction is announced, each node records the details of the transaction event in its ledger copy. Of course, this is a high level of what happens. The actual details of this kind of transaction processing we'll get into as we continue. The net effect is that every network node contains a redundant copy of the network's transaction history. This feature yields massively distributed data redundancy, if nothing else. This ledger, with all of the blockchain event history, would over time become a list miles and miles long with millions of individual transactions. Having so many individual entries can become unmanageable and even clunky. Many blockchain implementations break this list down into more manageable units. Transactions are grouped into smaller chunks called blocks. The number of transactions in a block depends on the specific blockchain, but we can think of a block as a small number of transactions from the overall ledger list. So, instead of simply individual transactions, the ledger is actually composed of blocks, which each contain transactions. These blocks are then linked together in a very specific way, one referencing the next, and the net effect is the chain of blocks we discussed earlier, or, more simply, the blockchain. With that, let's now talk a bit more about the network itself. Who are the participants in the blockchain network, and why do they choose to work together? If we introduce a bank example, we can identify the issues in placing trust in a third party to maintain a ledger of our monetary transactions, i.e. the bank. We can identify how risky it is to have a third party do this for us when it would be better to do it ourselves. As we all know, banks are not perfect, and we should know that blockchain technology has come to help us do this ourselves. Not only that, but blockchain's decentralized distributed architecture that enables massive data redundancy provides a much more secure venue for our transactional history than a bank, or any other centralized third party for that matter. This venue is designed to benefit its stakeholders versus a third party, which is organized to benefit itself. The participants in a blockchain network are not people, they're nodes, which are computers. The activities of these computers is orchestrated by software that each node runs, and the behavior of each node is then controlled by the protocol that that software dictates. The overall effect is that all network activity is predictable, controlled, and secure. The people who introduce nodes to the network do not have to know each other in any way. They only need to bring the node up on the system and be sure the computer is connected to the network. This is in high contrast to how trusted third parties operate, where anonymity is scarce. So, to get back to the original question of how do blockchains work, we've seen that blockchain data is essentially a ledger, or register, of events that have happened on the blockchain network. We learned that this list of events is broken down into blocks that each contain a portion of these events. We discussed how the blockchain network itself is composed of nodes, which are computers running software designed to support the network's protocol, and how each of these things together eliminate the need for a centralized third-party authority, like a bank, to keep track of events when a trustless organization like the blockchain can manage them much more effectively. Okay, with that and the preceding presentation of the steps we'll take to build our blockchain-based cryptocurrency, let's shift to getting our development environment set up so we can begin implementing these concepts and composing our crypto system. Join me in the next video where we'll introduce Code Anywhere, an online JavaScript IDE that will virtualize our development. If you're not familiar with it, it's really cool. Now we'll get into the coding portion of this course. We'll create a high-level implementation of a blockchain in JavaScript to materialize what we've learned up to this point and really drive home the core concepts from a basic code up. While we'll not build something that you can create the next multi-million-dollar ICO upon, we will create a basis for blockchain functionality and see for ourselves in our own code how some of these concepts can be implemented. I like to present coding concepts with an online IDE, so your experience and mine are exactly alike, regardless of whether you're working on a Mac, PC, Linux, Chromebook, or even a tablet. The preferred online IDE for this purpose is Code Anywhere, as you can create an account and be coding in minutes. The whole experience is great, as with Code Anywhere, you code in your own virtual server in the cloud. Code Anywhere creates a complete, stacked-up environment for us to work in, so we can completely disregard the concept of localhost. This keeps our own devices from being bound up with additional development config and overhead, and leaves the heavy lifting in the cloud, where we can access it from anywhere. If you've never used an online IDE, please join me on codeanywhere.com and give it a try. Chances are you'll love the experience and consider it for further development. Of course, if you love and are faithful to VS Code, Sublime, or Atom, or whatever, that's okay too, whichever you prefer. Give Code Anywhere a chance though, if you can. To get going on codeanywhere.com, just create a free account and bring up the IDE in a browser tab. The layout should feel familiar if you've used an IDE before. On the left of the screen is a tree view of the workspace, and there is a node called Connections. If you right-click this node, options will be presented, and you'll want to click New Project. This will open up a dialog that prompts you to name this project, call it JS Blockchain, and this window also allows you to configure the single container that the free Code Anywhere account type provides. In the list of container recipes, scroll down to the Node.js on Ubuntu option and select it. Then go back to the top of the window and name the container Node.js on Ubuntu. Excellent. Click OK and let Code Anywhere configure your new server and spin it up. When it's ready, you'll see the name of the container in a new child node of the Connections node in the left-hand side tree view. We've now got a fully configured server with Node running, not to mention MySQL and Redis, which we won't be using, and we're now ready to write some code. First though, we need to initialize our node environment by clicking in the terminal and entering npm init. Then we can name our project within the node, and then default through the rest of the init questions. Great. Let's do one install while we're here, as we'll need a JavaScript cryptography library in just a few minutes. Enter the command npm install --save crypto-js. This will install the crypto.js library that we'll depend upon to do the hashing things we'll need to perform in a little while. This is a cryptographic utility for JavaScript. It will assist us as we write blockchain code in the next few videos when we need to encrypt data. I'll say now that crypto in general is hard to do correctly, very hard to do correctly. Using crypto libraries in JavaScript, or any other runtime environment for that matter, exposes a large surface for attack, and reducing that surface is a job for the experts. So, as we employ the crypto.js library, do not think in any way that we're producing a production-grade security implementation. Not at all. We're introducing the use of a cryptographic utility in our code and seeing how various encryption algorithms change string values to hash values. That's all. The efforts and techniques that the big boys who develop major blockchain systems put forward are a lifetime study and are far, far beyond the scope of this course. So with that, let's check out the crypto.js documentation. We can go to the npm.js page that describes the package. Here we can see that this is high-leveled as a JavaScript library of crypto standards. That's good, but what does that mean? As we scroll down, we can see the package is used to perform HMAC level 1 SHA hash on messages with a key parameter. That is telling. Further down, we can see how a SHA-256 hash is performed on a string value to create an encrypted value. We're starting to get the picture here. The actual API doc can be found at code.google.com/p/crypto-js. Check it out too if you're curious. If we continue down the npm.js page, we'll see some code illustrating actual usage of various hashing functions. We can see the use of the AES cipher, where the crypto.js object provides the static hashing method. And with AES, we can see that a key is used to encrypt and decrypt. The implementation couldn't get much simpler. Just pass the string to encrypt and the key as arguments. And the same thing for decryption. Beneath that is an example of object encryption using the AES cipher. We can see that we simply use json.stringify to format a JavaScript object as a JSON string value as it is passed into the encryption method. Then we use json.parse as we decrypt the hash to recreate the object. This is very simple usage and shouldn't confuse anyone. As we work with the library, we'll use SHA-256 to hash our objects and values for the blockchain. As we aren't using keys in our implementation, SHA-256 can be performed by simply passing the value to be hashed into the crypto.js object's static SHA-256 single argument. This will do the job we need done, as we'll see. Okay, we can now get Angular installed and our dev server configured so we can test our code and UI as we develop. To have Angular and its CLI installed and function correctly, we need to be sure we've got the current version of Node running in our environment. This takes just a few commands. The first is to install the latest Node version. The command is nvm install node. When it installs, we can use the command nvm ls to see what version was installed. Each installed Node version is listed, and our new one is highlighted. The third command sets this new Node version as the default for our Code Anywhere instance. We use nvm alias default and then the new version number, which is highlighted in the list. This version of Node is now configured to be the default version within our environment. Okay, the fourth and final command will update our global npm version so it is in parallel with our default Node version. We use npm -g for global and npm, and this will install npm globally and will be used in parallel with our current Node default. So we let this finish. And great, Node and npm are all updated, and we're ready to install Angular through the use of its CLI tool, which does so much of the Angular heavy lifting for us. The CLI is awesome and saves us from many manual processes in getting Angular up and running. The command to install the Angular CLI is npm install -g at angular/CLI. This installs a ton of dependencies and takes quite a while. When it completes, we can use a single command to have the CLI set up and scaffold a fully functioning project for us. Like I said, the Angular CLI tool is awesome. The CLI new project command is ng new and then our project name. We can use ng-crypto as the name of our new Angular project. ng is short for Angular, if you didn't know that. The CLI tool will do a number of things with this one command. It will download Angular and all of its dependencies, a ton of stuff. It will scaffold the project for us, including all of the best practice, folder structures, and config files, and will generate a simple working project that we can immediately try to run to prove our installation successful. Okay, with the installation complete, because we're working in Code Anywhere and do not have a local server for development, but instead we'll have our dev server running on our Code Anywhere virtual instance, we need to make a single tweak to the package.json file that controls our node setup. If we open the file by double-clicking on the Node.js entry in the left side tree view, we can adjust the start serve node of the scripts entry. After the colon, we add the following: ng-serve --host 0.0.0.0 --port 3000 and then --public and then our connection name, our Code Anywhere username, and then .codeanyapp.com. This indicates the dev server running at IP0000, or within the virtual host, if you will, a port of 3000, which we can use on Code Anywhere to enable HTTPS, and then the public value lines, which set up our dev server with the way Code Anywhere makes apps available from an external browser, as we'll see. With these settings all done, we can save the package.json file and fire up the server from the terminal. Let's be sure we're in the directory that the Angular CLI tool created for our app, and then we can use the command npm start, which will fire up the server. We should now be able to go to the correct URL and see our app running the simple thing that the CLI generated for us. To find the app, in this tab, we can see the HTTPS URL where our app will be found. Let's click that URL and see. And yes, our app is running properly, and we can assume that the CLI installation was successful. Great work. With that overview of our crypto package, Crypto.js installed, and Angular installed and set up, let's move to the next video where we can start building the basis of our crypto project, a blockchain class, and its accompanying block class. With a plan of action in place, let's begin writing up our JavaScript-based blockchain project. In our Angular project, within the app directory, let's open the app.component.ts file. And the app.component.html file. These two files make up the initial component of our current Angular app. The CLI created this for us and connected it to the application's foundation construct, which consists of index.html, main.ts, and the app.module.ts files. These three files get the Angular project up and running when we fire it up with the npm start command, and then engage the two files we just opened up, app.component.ts and app.component.html. As we work with these files, we need to understand that Angular does everything in terms of components. A component is a UI template attached to a supporting file that has logic to control the HTML and JavaScript elements expressed in the template. We'll use this app component exclusively to build out all of the UI for this project. Usually, many components are composed to create an app's UI UX, but we're pretty limited in what we plan to do in this app, and we want to keep things as simple as possible. So we'll just do everything in a single component. Cool. So let's clean up the boilerplate stuff in this component's template file. From within the app.component.html file, let's strip out all of the UI elements except the title, which we can change in the backing code file. For now, we'll just clean everything out of this file. Notice for the title element, there are double curly braces and a variable name between them. This is a binding to the variable, as indicated in the backing file. These double braces are commonly referred to as mustache syntax. This is the link between TypeScript code logic, class properties, variables, and service instances in the backing file, and the display of all of their values here in the UI. Angular makes binding like this quite simple. In the backing file, app.component.ts, let's talk a bit about how this component file is set up and how its lifecycle works. First, we can see at the top of the file that a component reference in Angular core is made. This provides the properties and methods that an Angular component requires. Then we can see what is called a component decorator, which starts with @component. This is where we can define various attributes of this component. Here we can see the selector, which is how the component is referenced in HTML files, the template URL, which points to the components.html file, where the UI is defined, and the styles URL, which points to a file that will style the element in this components.html file, the one specified right above it. Okay, the following lines should look more familiar. While this is TypeScript code, the syntax shown here is, for the most part, common JavaScript. Great. In this code, we can see a variable defined for our app title. This is the variable that is referenced in the template file within the mustache syntax, as we saw. We're now familiar enough with the files that create an Angular component, our app.component in particular, and we can feel comfortable coding within these files. We now need to define our blockchain and block classes within our project. Keep in mind, this should be done in an Angular-specific way and will be written in TypeScript. The best practice for classes that will be used app-wide is to define each class in its own TypeScript file, which can then be referenced whenever necessary from any other application class. Custom class files in Angular typically reside in their own directory called classes. We can create this directory from the command line with make directory classes. Then we can create the class files we need with the following: touch blockchain.class.ts, and touch block.class.ts. Notice the file name convention. We use .class.ts to indicate that these are class files and that they're TypeScript files by using the .ts extension. We can see in other existing file names, like the app.component.ts file and the app.module.ts file, that the nature of the file is indicated in the file name with the .whatever file kind indicator. These conventions are used by various Angular infrastructure utilities, so following this file naming convention is required for best performance. Okay, we can now begin fleshing out these two class files. Let's look at the block.class.ts file first. We can double-click it to open it in the editor. Our first step in creating a blockchain system is to bring in the crypto.js library. We do this with the following code in the first line of the block class file. In Angular TypeScript syntax, the code looks like this: import star as SHA-256, from crypto-js/SHA-256. This references the crypto.js library's SHA-256 module and creates a reference called SHA-256. This is TypeScript syntax in action. Next, we define the class itself with more TypeScript. Here, we're using the 4 parameters to instantiate a block class. Within the constructor's body, we're assigning these parameter values to class properties with identical names. Because this is TypeScript, we define the type of each of these values as well. We can use any as a type when we don't want to be specific. It's kind of a cop-out, but it's okay for now. Finally, to finish this class off, we can add a calculate hash function, which will hash the block and give us the equivalent of a block header value that can be used in block linking. So we'll create the function calculate hash, and then return the function SHA-256, and the parameters for this function are this.index plus this.previous hash plus this.timestamp plus the data, which needs to be stringified. So we use json.stringify and then pass in this.data. And then we take all of this to string. Great, that is our current block definition. We've got this defined for use in the blockchain class. Join me in the next video where we'll code this class up. With our block class all ready to use, we can now define a blockchain class that will implement our block class as it creates an actual linked blockchain instance. We can double-click the blockchain.class.ts file in the left-hand tree view and add the crypto.js/SHA-256 import like we did in the block class. Then we can add another import for the block class itself as we will need it in this class. We use import block from ./block.class. Then we define the class signature. We need to define two properties: chain, which is an array of block objects, and difficulty, which is a number that we can initialize to 0. Excellent. So, as with any blockchain, the first block in the chain is called the Genesis block. That kind of kicks off the party. It's not a typical transactional type, so we need to create it manually. Let's define a function that will properly create this Genesis block for us. Below the constructor, the function should look like this. Create Genesis block is the function signature. And then we'll have it return new block. And the arguments for the block are 0, a date of 15/01/2018, the third parameter is Genesis block, and the fourth parameter is a string with a 0 in it. Here we have the function returning a block instance with an index value of 0, a date of January 15th, 2018, and a previous hash value of 0. As this is the first block in the chain, it doesn't link to a previous block, so 0 works as an indicator of that condition. Its index is also 0, obviously. Great. Let's now call this function in the constructor, so whenever we create a new instance of this blockchain class, the necessary Genesis block is automatically set up. In the syntax of this function call, we can implicitly create a property called chain as an array of block objects, which will represent the blockchain itself. We can add the following to the constructor's body. This.chain equals an array, and within the array brackets, we say this.createGenesisBlock. As we will always be needing the latest block on the chain, as we introduce new blocks to the chain, we should have a function that retrieves that block for us. Let's make a new function called getLatestBlock that will give it to us. This can simply return the last block on the chain by using the length of the chain as a gauge. So we'll set up a new function called getLatestBlock. And then we'll have this function return this.chain. Then we'll use brackets to reference the array, and the block that we want, we get with this.chain.length minus 1. Excellent. Now we need to be able to add a block to the chain appropriately. A function for this will need to take a newly created block as a parameter and be able to add the hash value of the latest block on the chain to the new block's previous hash property. This will then tie the new and latest block together to create a chain link. The new block then needs to be hashed with the previous hash value included so it can be put on the chain. When that is done, the block can be pushed onto the blockchain object's chain property array. So we set up a new function called addBlock, and we pass in the parameter newBlock. And within the body, we take that new block and we get its previous hash with newBlock.previous_hash. And we set it equal to this.getLatestBlock.hash. The next line, we say newBlock.hash equals newBlock.calculateHash. This sets the new blocks.hash property to the output of the calculate hash function. And then the final line, we say this.chain.push new block to push that new block into the blockchain array. Okay, we've now got a blockchain set up that we can actually test. Let's create the additional items we need. Let's save this file off, and then we can define a new Angular service. An Angular service is a class that is used to hold data access and processing logic. We use a service to get external data from an API or a database, for instance. A service can also have functions for processing that data, possibly along with additional data points. Services generally run as a singleton in the application's root context, where they can be accessed by any component. Back in the terminal in the app's home directory, we can use the CLI to generate a new service for us. We'll define a service called Crypto that will do our blockchain processing for us. It will maintain our blockchain class instance, and we will access it from our app.component to display the blockchain data. We use the terminal command ngg service services/crypto-m app.module. Ng engages the CLI. G means generate. Service is the type of class that we need generated. Services/crypto is the location we want this new file placed. And -m indicates the module that we want to register this service within. We've chosen app.module, which is our app's root module, so our service will be registered in that module and will be available in the root context for any component that needs to reference it. With our new service generated successfully per the output, we can refresh the source directory in the tree view and see our new services directory. Within it, our crypto.service.ts file now resides. Let's open that file up and fill in our logic. Here we can see injectable being imported. This is necessary as we need to inject services into the classes that use them. We'll get to that shortly. We need to import our blockchain and block classes next because we will use both of these classes in our service code. The import syntax looks like this: import blockchain from /classes/blockchain.class. And then import block from /classes/block.class. With that, we can see that the class definition is decorated with the injectable import. Within the class definition itself, we can add our blockchain code. We can first define a crypto chain property of type blockchain, which we can initialize as a new blockchain instance. Then, within the constructor, we console log a starting to mine a new block message. And then we can add a new block to the crypto chain property. We use the blockchain class's addBlock function and pass in a new instance of a block with index 1, a date, and an amount of 10. Cool. Let's add another block in the same way. Okay, we've now got 2 blocks being created and added to the blockchain in our new crypto services constructor. To have this service actually fire up and work, we need to reference it in a component. Let's go to the next video where we can wire up this new service within our app.component.ts class. In the last video, we got our crypto service all set up, and we now need to wire it into our app.component.ts class so we can access the service's blockchain property in our UI. Let's do that now. We've got our single app.component component in which we can import this service and then reference its crypto chain property. This will ensure that an instance of the crypto service class is created and available, which will fire the object's constructor, which will in turn create a new blockchain object for us and add the 2 new blocks. We can then display the blockchain data in our component. Let's go back to our app.component class and define a blockchain property on it. We can give it a type of string and initialize it to empty string. Cool. Then in the class's constructor, we'll add a parameter of an instance of our new crypto service class. This constructor syntax will inject the service into this component object where it can be referenced. We will also need to create an import reference for this service at the top of the file. So first we'll add the blockchain property and set it to empty string. And then in the constructor, we'll pass in our crypto service. We'll say private, so the service can only be used in this component. Crypto service, and a colon, we'll make this of type crypto service. And then at the top of the file, we'll add the import of crypto service. from /services /crypto.service. Okay, now within the constructor's body, we can add a line that will access the service's crypto chain property, then stringify it, and then assign it to the blockchain property defined in the component. Excellent. With this blockchain property defined and set, we can now bind to it in our components template. Let's look again at the app.component.html file and use the template syntax to bind to this blockchain value. In the template, below the title div, let's add another div. Within these tags, we can add the text, "Here is our current blockchain." Then we can use double curly braces to bind to the blockchain property in our component backing file. Great. This will now display the contents of our blockchain on the page. Let's save this. And then the service file, and see if we get a good compile. To do that, we go to the Terminal tab. If the Angular dev server isn't running, use npm start to bring it back up. If your Terminal tab is not responsive, go ahead and close it out and open a new one. If you do have to open a new one, be sure to change into the application's root directory. And again, it's npm start to bring up the Angular dev server. Then we wait to see the output of the server log, which will tell us if our app compiles properly. Things should be just fine. If not, the issue is most likely a fat finger error somewhere. Look in any displayed errors for the exact location of an issue. When a compile completes successfully, we can go to our browser and see our app running. Here in the browser, we can see that we've got a blockchain object that contains the blocks our code created. We can look closely to see if the hash links have been created properly and our chain is valid. Within each block, there's an index value 0, 1, and 2, and that looks good. If we look at the last block, in its previous hash property, there's a hash value with these characters at the start. If we look at the previous block's hash property, the hash starts with these same characters. So we can assume that the blocks are linked correctly with that complete hash value. Then we can look at this block's previous hash value and see that it contains the Genesis block's hash. Great, our blockchain is valid. We've now validated our blockchain manually, and that's cool, but validation should be done programmatically and automatically. So let's add a new function that can validate the blockchain class for us. Let's add a new function called isChainValid to our blockchain class, which will give us a Boolean value. This function should be able to iterate the blocks in the chain and validate the hash and previous hash equality condition for us. So we can define the function called isChainValid. And inside the function body, let's add a for loop that sets up an index beginning with 1, as we don't need to validate the chain's Genesis block. Within each iteration of this loop, we need to grab the block at the location of the loop's index and then grab its predecessor on the chain, which is the loop index -1. We then have our block under test and the block prior to it in the blockchain. The test logic we need to perform should take these two blocks and do two things. First, it rehashes its own content and checks that hash value against its own .hash property. This is a test for the validity of the block's contents. These hash values should be the same unless the block's properties have been tampered with. If the block passes this check, we can then check its link to the previous block in the chain. We can grab the block's .previous hash property and then compare it to the previous block's .hash property. If these are equivalent, we can move on to the next loop iteration. And then after the loop structure, we can return either true, provided all checks passed, or false, if one or more blocks were mutated. Okay, let's run this function to programmatically validate our blockchain. We can actually code all of this in the app.component.html file with template syntax. In the template file, let's add a new div. Then within it, we can add h2 tags and say blockchain state. Then we add a nested div, and within it, use Angular template syntax that will check the state of our blockchain with the isChainValid function of the blockchain class. We do this with Angular's ngIf directive. If the condition is true, meaning our block is in fact valid, we can have it display a chain is valid message. Then we tack on an else conditional within the ngIf statement and have a different UI template display if the condition is false, meaning our chain is not in a valid state. Below the directive line, we can add an ng template with an identifier of invalid blockchain. And then have this template display an invalid state message. As we can see, Angular's template syntax is easy to work with. Here, we've kept all of this blockchain validity display logic in the template. Nice and neat. Let's save this template off and see what our page looks like after Angular compiles the new code and reloads the page. And we now have our automated blockchain checker working and it shows us that the chain is in fact valid. Excellent. We've got our blockchain working nicely and are able to successfully add new blocks while maintaining chain validity. Let's go to the next video where we'll move to the next step in our project's evolution by introducing proof of work to our blockchain. As we've proven, our blockchain class can be instantiated and used with our block class to create good blocks and maintain chain validity. We can now focus on another general blockchain concept, the gatekeeping security measure called the proof element, which keeps blockchains consistent, complete, and unalterable. This component of the blockchain formula is normally manifested in mining activities. Miners will ensure that new transactions are true, relevant, and valid prior to submitting them to the blockchain, but are kept from doing so on a rapid-fire basis by this proof protocol. This keeps the blockchain from overloading and keeps irrelevant transactions, or spam, from littering the blockchain data. Proof is an economic measure that wards against DDoS attacks and other service abuses by requiring some form of value from the miner. In the case where proof of work is implemented, this value is in the form of CPU cycles. To be accepted by the rest of the network, a new block must contain a so-called proof of work. The actual work that is performed is in solving a cryptographic puzzle. This concept is also referred to as CPU cost function. The puzzle miners must solve includes finding a number called a nonce, such that when the block content is hashed along with the nonce, the result is numerically smaller than the network's difficulty target. The difficulty target is an adjustable number used in maintaining network activity levels. This proof is easy for any node in the network to verify, but extremely time-consuming to generate. As for a secure cryptographic hash, miners must try many different nonce values before meeting the difficulty target. We can think of this as repeatedly hashing the block's contents and checking to see if the resulting hash value starts with a certain number of zeros. Enough zeros at the beginning of the hash value will solve the puzzle. The number of zeros required is relative to the current difficulty level set by the network. The nonce value is used to make each hash computation unique. Miners will begin with a nonce of 1, append it to the block content, hash this value, and check how many zeros are at the beginning of the hash value. Having zeros at the beginning of a hash value is quite rare, so this process is recursively performed, each time incrementing the nonce value, appending it to the block content, hashing, and again checking the resulting hash value. This takes billions upon billions of recursions to finally arrive at an acceptable hash value and suffice the block's proof of work requirement. All of this work to be able to submit a new block to the blockchain. In the case of Bitcoin, miners are monetarily rewarded for submitting new blocks, so the mining incentive is built into the system protocol. Successfully mining a Bitcoin block yields new Bitcoins to the network. The miner is awarded those coins for doing all of the mining work. Plus, the miner is rewarded any fees paid by the users who create the transactions within the mined block. A pretty sweet deal. This is why the crypto mining space is currently so hyper-competitive. As a concrete example, let's solve for a proof of work with block content consisting of just the sentence, "The quick brown fox jumps over the lazy dog." We'd figure out a nonce strategy and begin recursive hashing until we find the nonce that yields a hash starting with 4 zeros, assuming a difficulty level of 4. First, we start with "The quick brown fox jumps over the lazy dog 1, which has an MD5 hash value of this. This doesn't start with any zeros, so we increment our nonce, assuming our nonce strategy is to add 1 to the previous nonce value, and then try "The quick brown fox jumps over the lazy dog 2, and then 3, and then 4, and 5, and so on. As it would pan out, none of the hash values start with 4 zeros until we get all the way up to a nonce value of 49,609, which has a hash value of this. The only way we could possibly find the nonce value that gave that hash a value with 4 leading zeros was to keep trying hashes with an incremental nonce value. There's no shortcut, we have to do the work. After a successful proof of work solution is found, and a miner submits the proven transaction to the network, the solution needs to be validated by other miners. For a miner to validate the proof of work on a transaction, the nonce value used to find the acceptable hash is used to quickly hash the block content and the validation is complete. No recursion involved. So in our example, the validating miner would just need to get the hash of the quick brown fox jumps over the lazy dog 49609, which yields this hash value. If the transaction were submitted by a rogue miner without a nonce that effectively hashes the block's contents, the block is disregarded in its current state and is sent to another miner who can then proof it correctly. All of this effort, technology, and resources work well to serve the needs of blockchain security. It may seem like a very elaborate scheme, which it is, but without a gatekeeper and the easy validation path that proof of work provides, just like with the many other pillars of the blockchain formula, the blockchain would be worthless. What's more incredible is the fact that more often than not, there are multiple miners trying to mine the same block at the same time. They're typically involved in a race to see who can solve the block the fastest, as the winner is awarded the Bitcoin prize. So not only are all of these resources used as a miner solves a block, but multiply all of that times 10, 50, or thousands of times for each block on the chain. The Bitcoin network has tens of thousands of active miners, each working on the current block, an amazing amount of resources to keep the network secure. There are other ways to implement proof in blockchain systems. Proof of work has been very controversial as it requires so many hard resources in the case of popular networks like Bitcoin, where the difficulty level is so high and miners spend hundreds of thousands of dollars on special mining hardware. The waste of energy in proof of work mining is hard to justify as well, especially when other proof designs are readily available. Fortunately, many newer networks have flown clear of proof of work for other approaches. One that is commonly used is proof of stake, which doesn't require massive hardware, computations, and power. With our blockchain project defining a blockchain object and a way to add blocks to it, we need to now add the ever so important layer of network security. We can do this with the proof of work protocol and create the proper measures to curb spam and keep our transactions relevant and immutable by forcing those who submit transactions to the network to make a commitment of work prior to allowing those transactions onto the chain. Our proof of work implementation will loosely introduce the concept of mining to our project as the functionality of our blockchain improves. To get this concept going, we can return to the block class file and focus briefly on the hash property. We can see that its value is set within the constructor through the use of the calculate hash function. Excellent. We'll use this property as we add in our proof of work logic, which we can do now. Still within the block class, let's add a new function called mineBlock. Now, because we have some potentially long-running processes in our mining activity, we'll need to get asynchronous and have this mineBlock function return a promise. This function will take a parameter called difficulty, which represents the difficulty value we will place on our proof of work cryptographic puzzle. Of course, this puzzle will require a certain amount of zeros at the head of the hash's output value to be considered acceptable. We'll have to include a mechanism to iterate the puzzle's logic until an acceptable hash is found. We can do this within our new mineBlock function with a while loop. In this loop, we'll take the first characters of the hash our cryptographic puzzle emits and check them to see if the hash is acceptable. We use while, and the while's condition will be this.hash.substring with the arguments of 0 and difficulty. And then we'll see if this is not equal to array. And within the array, we have difficulty plus 1. And we use .join and pass an argument of a string value of 0. And this will evaluate the hash string by taking from the first character in the head of the string to the value of difficulty. So if our difficulty factor is 4, the first 4 characters of the hash will be checked for zeros. As this is the condition of our while loop, the hash will be continually generated in iterations of this loop until we see an acceptable count of zeros in the hash's leading characters. So now, within the loop's body, we need to hash our block. We can say this.hash equals this.calculateHash. Then after the loop, we can call resolve as we've found our winning hash. At this point, we need to introduce the nonce concept that we discussed earlier. Our loop will now just continually hash the same value and never resolve. So we must plug in a nonce and increment it with each loop iteration and progress through the nonce values until the correct nonce is found that will give us an acceptable hash value. Let's add a property in the block class for a nonce as a type of number and then default it to 0. Great. Now we need to put the nonce value into the block's contents, so when the hash on the block is generated, the nonce is included. Within our calculate hash function, we can add the nonce value to the stringified data object to have it included. Let's add plus nonce to the JSON stringify this.data portion of the return statement. Excellent. And finally, the nonce value needs to increment with each iteration of our mindBlock function's while loop. So let's add this.nonce++ before the calculate hash line in the loop's body. Cool. Now we can look at our blockchain class and see how we can implement our new block class's mindBlock function. If we look at the blockchain class's addBlock function, we see that it is getting and setting the previous block's hash on the passed-in new block, calculating the new block's hash, and then pushing the new block into the chain array. That's good, but we can now use our mindBlock function instead of calling the calculate hash function on the new block. Let's change this line to newBlock.mindBlock. This will work properly with our new code. We also need to change this function's signature by passing in the difficulty factor as a parameter. So we can add this.difficulty as a parameter. This difficulty factor is now referenced twice, but hasn't been set yet. Let's set this blockchain class property to a value of 3 as we test our new code. We can always raise the difficulty later when we're done testing. Let's change this difficulty property to a value of number 3. Great, now we can test out our new code. We can save this file off, and Angular will compile it and reload the app in the browser with our new changes included. And in the DevTools console output, we can see the 2 blocks were successfully mined and that the resulting hash on each block has 3 leading zeros, as we had set the difficulty factor to number of 3. These blocks were mined pretty quickly, probably too fast for providing enough security, but for our purposes here, 3 works fine, and we are proving our proof of work implementation. Great. We've now got our proof of work implemented in our blockchain project, so let's move to the next video where we can get the rest of our mining protocol defined and working. With proof of work implemented, let's now upgrade our blockchain project with some more realistic mining functionality. We can do this by including the ability to pay out mining rewards and be able to process multiple transactions within a block. Our current implementation only allows a single transaction within a block, which kind of defeats the purpose of the block. In adding mining rewards, we're also adding the ability for the blockchain to mint new coins and introduce them to the users of the system, not unlike how Bitcoins are minted. We'll give the miner of each block a coin reward that can then be sent to other users as our cryptocurrency blockchain comes alive. First, we can upgrade our block class so it can handle more than just a single transaction. We can do this by changing the data property from a string value to a transactions type array. This array will contain transaction objects, which we'll define shortly. So let's change the property name and assignment in the constructor, and then update the data parameter name to transactions, txns, as well. We'll also have to update the argument in the calculate hash function that references the old data property name. Okay, we can also eliminate the index parameter and property as we no longer need this reference. Instead, the index of each transaction in the transactions array will suffice for our purposes. Let's delete the index parameter and property, and then remove the index reference in the calculate hashes SHA-256 function. Great. Now, in our block class, our new transactions array deals with transaction objects, so we need to define a transaction class that we can use. Let's go to the classes subdirectory in the left-hand tree view of the IDE and right-click on the node to get a Create File option. Name the file transaction.class.ts to maintain Angular convention. Then we can define properties of this class of timestamp, payer address, payee address, and amount. We can make all of these of type any for now, except for amount, which should be of type number and a default value of 0. Okay, then in the constructor, we can have all of these values passed in and then assign the parameters to the properties defined on the class. We can save this new transaction class off. And then we'll need to import it into our block class. Back in the block class, at the top of the file, we'll say import transaction from /transaction.class. And then we can go over to the blockchain class and import this transaction class as well. Excellent. Now we can update our blockchain class so it can pay out a reward to a miner who mines a block, and then we need to add a new function that will execute mining logic on the unmined transactions that have been sent to the blockchain for processing. We also need to add a property that will tell the mining function how many coins to reward the miner. So let's add the property mining reward, use :number to set the type to number, and then we'll say 50 coins. Cool. At this point, we can update the blockchain class's add block function with new mining logic. Instead, let's completely replace this function with a new one called mine current block. So within the function's body, we need to first instantiate a new block by passing in a timestamp, the unmined transactions, and the last block's hash as parameters. Let's say let block equal new block, date.now, transactions, and this.getLatestBlock.hash. All right. Of course, in systems like Bitcoin, miners select the transactions that they want to mine. They'll typically choose the highest Bitcoin yielding ones first to maximize revenues. In our case, though, we'll simply have the miner take all unmined transactions, regardless of their content and properties. With a new block created and the transactions assigned to it, we can go ahead and mine it. Let's add another line like this: block.mineBlock. And we'll pass in the difficulty. We're passing in the difficulty factor value that we defined a few minutes ago. Okay, now, as mineBlock is a synchronous function, we can add a console.log beneath it to update the console with the mining status. Let's add console.log and pass in the message current block successfully mined. And finally, we can push this newly mined block onto the chain with this.chain.push, and then we pass in the block. Great. Before we're done here, though, we need to do some refactoring and some accounting. Let's move to the next video where we can make these two significant updates and then get our code ready to test out. We've got the bulk of our mining process coded, but we still need to do some refactoring and accounting in our blockchain class's mineCurrentBlock function. First, let's do the accounting, meaning we need to pay out our miner for successfully mining a new block. We can simply create and add a new transaction to the passed-in transactions array to pay out the block's miner. So let's update the mineCurrentBlock function by adding in a new transaction to pay the miner, like this. Cool. Notice we're saying the source of the coins are from the mint. This way, we'll know this was a mining payment transaction that created the new coins. Also notice that we're referencing the miner's wallet address in the third parameter of the new transaction. The mineCurrentBlock function needs another parameter, the wallet address of the miner. So when the mining reward is paid, there's somewhere to send the coins. Let's add miner address as a parameter to this mineCurrentBlock function. Great. Now our miners will gladly receive payment. All right. As the value of a user's wallet balance is something that is requested quite often, we should have a function for easily getting this value from the blockchain. As we know, or should know by now, the property of a wallet balance isn't included in crypto blockchains. This value has to be actively obtained from the transaction data each time it is requested of the blockchain, because the only information persisted on-chain are coins sent and coins received. We can make a function that computes a user's wallet balance by iterating all of the transactions in the blockchain and finding all of the users' send amounts and received amounts, and then computing them for an actual balance. Let's create a new function called getAddressBalance, where we can pass in the wallet address in question. This function can then iterate the blockchain's transactions and compute the balance for the passed-in address. Let's add getAddressBalance and then pass in an address. And then within this function's body, we'll first create a variable for the balance value. We'll say let balance equal 0. Then we'll have to loop through all of the blocks in the chain, and then for each block, loop through all of its transactions. Let's create the outer loop first. We'll use for, and we'll say const block of this.chain. This is TypeScript for loop syntax. Then we can add a nested loop. And we'll say for const transaction of block.transactions. So with this double for loop, we'll first be looping through all of the blocks in the chain, and then within each block, we'll be looping through the transactions within the block. Okay, within the nested loop, we'll see each of the blockchain's transactions. On each one, we want to check to see if the payer's address matches the passed-in wallet address. If it matches, we want to subtract the transaction amount value from the balance variable's value. Then we need to see if the transaction's payee address matches the passed-in wallet address. If it matches, we add the transaction's amount value to the balance variable's value. This will debit and credit the balance variable value until all transactions involving the passed-in wallet address have been accounted for. Finally, after the outer loop, we can return the balance variable. Great, we've added a lot of interesting logic and are approaching a functioning cryptocurrency. The last thing we need to do with our blockchain class is to refactor our Genesis block creation function. We need to use our transaction class and create a new instance of it. So let's start by changing how the constructor kicks off the create Genesis block process. Let's change how the chain variable is defaulted. It should just be assigned an empty array. Okay, in the create Genesis block function, we need to first create the Genesis transaction. We can define it locally, and give it a payer address of mint and a payee address of Genesis. Then the Genesis block needs to be created, so we can define it locally as well. And send in the transaction we just set up, and give it a previous hash of string 0. Great. Now we can push that block onto the chain, and we've got a Genesis block generating automatically. Very cool. With that, our upgrade is complete and we have a cryptocurrency system in play. Let's save this file off, and then before we go any further, let's keep the difficulty factor at 3 so we don't have to wait too long as our script executes. Okay, let's go to the crypto service file where we can add some testing code. We'll need to import the transaction class as we'll be using it within the constructor of the service. Use the following: import transaction, from //classes/transaction.class. Then let's delete all of the code in the constructor as it is now irrelevant. To test these new changes out, we need to create some new transactions to be mined. We'll first need a container for the transactions that are created so they can be passed into the mineCurrentBlock function in one fell swoop. Let's add an array of type transaction to the properties of this crypto service. Okay, now let's create some transactions. Let's have Alice pay Bob 50 coins. And then have Bob pay Alice back with 25 coins. This adds 2 transactions where Alice pays Bob, and then Bob pays Alice back half. This is good, but nothing actually goes down until these transactions are mined. So let's get some mining going and get Alice and Bob their coins. Beneath the 2 transaction lines, we can add code that will call the mineCurrentBlock function of the blockchain class. We have to structure this call to expect a promise in return, as we've refactored the mineCurrentBlock function to return a promise. This will start the mining process where the 2 transactions we added are in the blockchain as unmined transactions and will be processed by the mining logic, replete with proof of work. We have added a miner wallet address of wallet miner49er, so miner49er can get paid his reward for mining the block, and then we also passed in the array of our transactions to be mined. While we're at it, we can check to make sure everything is working by getting Alice, Bob, and miner49er balances. Those numbers should tell us how things processed and if our mining logic is correct and accurate. Let's add a .then statement to the mineCurrentBlock function to subscribe to the promise it returns. Within the .then, we can use the following to check those balances after the block has been mined. And this will give us a nice set of transactions to test everything out. One last thing we need to do though, as we changed the createGenesisBlock function and assigned an empty array to our chain property in this class, we need to change the existing constructor to simply call the createGenesisBlock function instead of assigning a transaction to the chain array directly. Let's just review the code we wrote. Oh, we need to spell resolve correctly. You probably did, that's just me. Okay, now let's resave this file and the rest of them and see if we get a good build. And it looks good. Let's now go to the browser and check its console output to see if we have a properly functioning blockchain. And yes, our block mined successfully, and we can see that Alice has a total of -25 coins and Bob has 25. This makes sense as Alice sent Bob 50 and he sent her back 25. But Alice started with 0 coins, so she's currently 25 in the hole. What's curious is that Miner 49er has a 50 coin balance. Where did all of those coins come from? Actually, this is correct because Miner 49er was, in fact, credited his 50 coin mining reward for this block. As we can see, mining pays pretty well. All right, we now have a functioning cryptocurrency blockchain implementation project and can mint coins. We can reward miners for mining blocks and accept new transactions and check wallet address balances, all while being secured by a home-rolled proof-of-work algorithm. Great. Hopefully this exercise has helped in understanding how the concepts of blockchain technology work by actually using them in code. This has also proved how simple the blockchain implementation actually is, and clearly shows that the complexities are in the surrounding concepts that make a blockchain solution work effectively. Let's move now to the next video where we can make this fantasy cryptocurrency blockchain project a bit more realistic by adding transaction validation logic. With our mining logic complete and our miners getting paid out, let's be sure they are not only solving cryptographic puzzles, but are ensuring that the transactions they're sending to the blockchain are valid. We can introduce logic that checks for funds availability when an address is attempting to send coins to another. Obviously, that is the minimum we would want to validate in a cryptocurrency implementation. So we can do that, and so our users have some funds to start with. Remember, Alice is currently running a deficit. We can set up an airdrop when our blockchain instantiates. With that plan, let's go to the blockchain class and set up an airdrop first. So here in the blockchain class, we can introduce the concept of registered addresses. These would be the coin wallet addresses that users have made the blockchain aware of, so transactions can be sent from or sent to said addresses. Let's initialize the addresses we want to work with when we fire up our blockchain. So let's add a registered address property of type string array and default it to an empty array. Then, in the class's constructor, let's add a line that sets the registered address property with the user's wallet addresses. Wallet Alice, wallet Bob, wallet Charlie, and our miner, wallet miner 49er. Cool. Now, because these addresses should start out with some coins, so we can use them as we test our code, let's create an airdrop coins function that can send a fixed amount of coins to each of these registered addresses. Let's have it take a parameter of coins that indicates how many coins each address will be sent. Okay, within the function's body, let's set up a for loop that can iterate the addresses array. Then, within each iteration, we'll create a new transaction that sends from the mint to the particular addresses and assigns the passed in amount of coins. Cool. Then we'll need to push the transaction onto the unmined transaction array so it can eventually be added to a block. Okay, this will give everyone some coins. Then, after the loop, we can simply have these transactions mined in a new block by calling our mineCurrentBlock function. Done. Very nice. Let's have this airdrop happen every time we instantiate the blockchain. We can add to the blockchain class's constructor, after the wallets are initialized, a line that calls the airdrop coins function. Let's pass in 100 for the number of coins to send each address. Great, let's save off this file and test the airdrop logic. After Angular successfully compiles our changes and the app reloads in the browser, we can see that the balances all reflect an influx of 100 coins for each registered wallet. Good, the airdrop works. Now we can begin working on a validation mechanism. What we need to validate is that when a user tries to send coins from one address to another, that the user is, in fact, in control of at least the amount of coins that are being sent. We can do this by getting their balance with the getAddressBalance function that we've already written. Then, if the user has coins to spend, we'll let the transaction happen by allowing it to be put in a block. If not, the transaction is simply disregarded. Let's make this happen. Let's go below the mineCurrentBlock function and add a signature for a function called validateTransaction. We can pass the transaction in as a parameter. Okay, now within the function's body, let's get the payer's address. This is the user sending the coins. We can say let payer address equal transaction.payerAddress. Then we can get this address's balance with the getAddressBalance function. Let's say let balance equal this.getAddressBalance, and we'll pass in the payer's address. Now we're ready to see if this address has coins to give. Let's say if balance is greater than or equal to transaction.amount to see if the address's coin balance can cover the amount of the coins the user is trying to send. If the balance is greater than the send amount, we can return true. If there's a deficit, we return false, so the transaction cannot go through. Cool. Now with the validation logic in place, we need to implement it. Let's change the mineCurrentBlock function so it validates each unmined transaction before adding it to the current block. We can do this validation as the first activity in the function's body. Let's define a new array called validated_transactions with let validated_transactions equal empty array. This will take all of the valid transactions and will be passed into the new blocks constructor when the transactions have all been validated and the new block is produced. Next, we need to loop through the unmined transactions and validate each one. Let's use a for loop like this. For const transaction of this.unmined transactions. Okay, now let's define what happens with each transaction in the iteration. Since we will see transactions with newly minted coins, we need to be sure that these validate. The mint doesn't have a balance. It creates coins out of thin air, kind of like the Fed. So it will get a pass in our logic. We use if transaction.payeraddress equals mint validated transaction.push Then we push the transaction onto the validated transactions array. This will allow any transaction that shows the mint as the payer to be immediately pushed to the validated transactions array and be put into the new block. Next, we need to make sure when a regular transaction comes through, it is validated. Let's just add this as a condition in the if statement we just wrote. So we can add an or this.validate transaction. Now, any minted transactions will simply pass, and then any normal transactions will be considered as well. Let's add in a console log that will tell us how many transactions validated and are being placed into the new block. Below the for loop, let's say console.log, and the message validated transactions plus validated transactions.length. Okay, we should be good. With that, we want the block that is created, which happens in the next line of code, to include only the validated transactions. We can change the second argument to the new blocks constructor to instead include our validated transactions array instead of the passed-in transactions array. Easy. We do have to also update the line where we reward the miner. Let's be sure to change the passed-in transaction reference in this line to the validated transactions reference. Okay, let's review the code. Here's the for loop. If transaction payer address equals mint or validated transaction. Oh, and we need to push the value of transaction. Fat finger error here. Okay. And this looks good. We've got a mechanism for validating each transaction that is put into the blockchain by ensuring that each unmined transaction sent to the blockchain is tested for positive funding prior to it being processed in a block. Great. Let's compile it and see it in the browser's console. And in the DevTools console output, we can see that we first validated 4 transactions. That seems legit. This was the airdrop, which did have 4 transactions. Cool. But the second transaction output shows 0 validated transactions. What is this? There should have been 2 transactions validated here. One where Alice paid Bob, and a second where Bob paid Alice. Each of them had their airdropped coins, so these transactions should have validated. Why does it say 0? The code in our individual transactions is correct and functions properly. The issue lays in the way our Angular application is firing these transactions. When the app loads in the browser, our app.component component is initialized. This component in turn initializes the crypto service, which creates an instance of the blockchain class. As we can recall, the blockchain class's constructor performs the airdrop, which mines a new block. Mining this block takes a significant amount of time, in a relative sense, long enough that while it is being mined, the crypto services constructor creates the 2 Alice and Bob, Bob and Alice transactions and begins mining them before the airdrop transactions are in the blockchain. So when these two transactions are validated, they fail as both Alice and Bob do not have coins to spend yet. It's a timing thing per our current implementation that is causing the problem. If the airdrop block mining were completed prior to the other two transactions being mined, there would be no problem. What we need to do is not have the new blocks mined prior to the completion of the blockchain initialization process, which includes the airdrop. These transactions were for demo purposes only, and we can eliminate them from the constructor of the crypto service as we move along. In the next section of the course, we'll introduce the concept of the crypto coin wallet, which is the mechanism for generating transactions, not hard-coded ones as we now have in our service constructor. We'll be able to have our blockchain in the right state prior to allowing the wallet to create new transactions. Then, this issue won't exist. We've now completed this section of the course where we have brought up a functioning cryptocurrency blockchain implementation that can take transactions, mine them, mint new coins, reward miners for their proof-of-work contributions, and can validate transactions as they're mined. Let's move to the next section of the course where we will write and implement a wallet class to bring our crypto coin project one step closer to reality. Join me in the next course section. At this point in the course, we've arrived at the third section where we'll begin creating a wallet class, which we'll implement in our app.component component to have an actual UI where we'll create transactions versus having them generated in test code in our service class. With this, we'll create transactions via the UI and we'll eliminate the issue we encountered in the last video, where transactions were being created prior to the blockchain initialization and included airdrop. Before we get our wallet class going, we'll first get our Angular project set up with a styling library so the UI we create is functionally and visually acceptable. We'll add Angular's material library to the project, configure it, and then begin adding various classes to our app.component.html template file to make our UI UX work as we'd expect. After we get this styling library running properly, we'll create our wallet class and get it functioning. Then we'll wire it into the rest of the project so we can create transactions at will. Then our final step in completing our project will be to simulate activity in our blockchain environment as if other users were transacting on our crypto blockchain, exchanging coins and creating transactions that will then be mined and additional coins being minted into circulation. Let's get started with our material library configuration. In the IDE, let's first get a new terminal up and in the context of our application root. Here, we can use npm to bring the material library into our project. The command we'll use is npm install --save at @angular/material space @angular/cdk. This actually installs two things, the material library and the Angular CDK component developer kit, which is now a dependency of the material library. It is used for creating custom styling components. Some material components depend on the Angular Animations module in order to be able to do more advanced transitions. If we want these animations to work in our app, we have to install the Angular Animations module and use the Browser Animations module in our app as well. We will use the following command to install the Animations module, npm install --save at @angular/animations. There are some material components that rely on another JavaScript library called Hammer.js. This is mainly to support gestures. To be safe and avoid any possible errors, we can install this as well. Use the command npm install --save Hammer.js. Next, we can get a theme set up. Material requires that we specify and configure a theme for our styling to base itself upon. This is simply done with a single entry in our app's styles.css file. This is found in our app's root directory. Double-click this file node to open it in the editor. We can then add this single line to have a pre-built theme globally included in our app. Within the CSS file, we add @import and in double quotes @angular/material/prebuilt-themes/indigo-pink.css. With all of these libraries and modules installed and theming all set up, our next step in getting Angular Material working in our project is to import the browser animations module in our app.module.ts file. This will give us access to the animations module app-wide, so we can style any templates we create. In our apps/source/app directory, we can double-click the app.module.ts file to open it in the editor. Within it, we can add the browser animations module to the list of import references at the top of the file. We use import browser animations module from @angular/platform-browser/animations. This provides the module with a reference to the module's content. Then, we need to look at the file's @ng module decorator entries and find the imports item. Within this object, we add browser animations module as an array entry. So here within the ng module decorator, we find the imports array and we add browser animations module. Our next step is to add a few links to our project's index.html file's header. We need to have the page link to material icons and specific fonts that the material library's components will need to display properly. We add the following two link entries to the end of the index.html file's header section. As we can see, these links are both coming from fonts.googleapis.com. One is a CSS file, the other is an icon file. Now we're almost done. Our last step is to manually import all of the material component modules into our app so we don't have to reference them individually in each of our classes. Material requires every individual component styling module that is used in a component to be referenced with an import entry. This can get tedious, so a workaround is to import all material styling modules into a separate module, then import that module into our app's main app.module module. Then we can use any and all material styling modules as we please without having to create individual imports for every one we use. We'll see how significant this is as we begin using these UI components in our app. To get this done, we need to first create a new custom module in our app. From the command line, in our app's root context, we can use the following command to create a new Angular module and have it referenced in our app.module module, which is what we want. So we use the command ng module space modules / my dash material space -m space app.module. This command generates a new module called myMaterialModule.module.ts. Note the use of the dashes between words in the command. Angular will automatically camel case this module name and add module.ts to create an angularized file name for the module file. Then the -m app.module flag tells the CLI to reference and import our new module in the app's primary module, which is called app.module. Then our new module is all configured and ready for code. With that, we can now find our module in the app's root directory under the modules subdirectory. Let's double-click the module.ts file and get this open in the editor. Here we can swipe in the myMaterial module code, which is included in this course's downloadable support document. I'll paste this in, and we can see that all material component modules are included. We can save this file off, and now we can use any material module in our app.component.html file as we build out a cryptocurrency wallet, which we will begin doing in the next video. Please join me there. With the Angular Material Styling Library installed and configured, let's now get a new wallet class into play. This class will provide the functionality of a standard cryptocurrency wallet with features like get my coin balance, and of course it will also allow us to send coins to other wallet addresses. We'll have a login type of functionality as well, which in our case will be the wallet name that has been registered with the blockchain. We set that up in our code previously, and we'll keep it in place to facilitate the overall functionality of our project. Let's go to our app.component.html file and begin setting up our UI. The first thing we want to do is comment out all of the code we have in that file. Okay, now let's add the foundation styling component for a typical Angular material app, a toolbar. This will be placed at the head of the page with our material theme's primary color. The component will have our page title of Crypto Wallet and will be able to hold various navigation components, buttons, icons, and navbar triggers, etc. We can use the following code to get this into place. Here we've got a simple toolbar with a title in its first row, displaying from the left side. Then we've got a second row with the balance displaying from the left and two icons that are pushed to the right side. This code makes reference to some CSS classes, so to get this component to display as described, we'll have to add some CSS. In Angular, components can have their own unique styling. In our app.component.ts files decorator, we've specified a CSS file to contain this component's styling, app.component.css. Let's open that file and add the following to get our toolbar to style appropriately. We can use .crypto-icon and add in padding of 0 and 14. Then we'll say .crypto-spacer and we'll put a flex attribute in with 1, 1, and auto. Okay, we're good with that. Let's go back to the component's HTML template. We can see we've used mustache syntax to bind a balance variable in our component's backing file. Let's go into the app.component.ts file and add that property. We'll make it a type of number and default it to 0. So here we'll say balance number equals 0. Great, let's save this file, the template file, and the CSS file, and see if we get a good compile. All looks good, so let's go to the browser and see what this looks like. Excellent, this looks nice, and it's displaying as expected. Let's add our first crypto functionality, specifying the particular registered wallet in the blockchain that we want to work with. Let's first add an additional material component, a text box. Let's go below the toolbar and add the following code. We first create div tags. Then within them, we create material card tags with mat-card. Note that all material components are prefixed with mat-. This mat-card tag is a styled container for the form we'll create within it. Inside of the mat-card tags, we can use mat card title tags and create a title for our card. Then we use mat card subtitle tags to include some directions for using the form. Then we'll use mat card content to hold our form. Within these content tags, we'll add our form element and the metadata that we need for this form includes the form group, which we call wallet address form, and we'll turn off autocomplete and auto validation. Okay, now we can add the single form field that we need. We use mat form field tags and add some additional styling. Then, within these form field tags, we can add our text box. Material syntax for a text box is simply input, but we add our details in the element's attributes. We add mat input as an attribute, a placeholder of wallet address, which will label our text box, and then we add a form control name of address, so we can reference this element in our backing code. And finally, we make this input required. Cool. Next, we can drop below the mat card content tags and add a new set of tags called mat card actions. This is a container for our form's buttons. Within these tags, let's add a button. This button needs a mat raised button attribute and a color of primary. When the user clicks this button, we will fire an assign wallet address function. We can add an icon to the button with an array label of assign a wallet address. The icon is account circle. And finally, we'll label the button with assign. Okay, this should be good for the template file. We need to go into the backing file and add in the things that we've referenced in the template. First, let's set up our form references. In the template, we refer to a form group of wallet address form. So we need to define that here. Above the title property, which we can now delete, we add the property wallet address form form group. Then we can go inside the constructor body and set up the form validation, as we do have our single text box set as required. Within the constructor's body, we can add this.wallet address form equals this.fb.group. And then we pass in an argument, which is an object address : and this is an array. Within the array, we have a single quotes entry and a validator's required entry. This references our form and uses Angular's form builder service to build out our form with validation. We need to add the form builder service as an argument for our constructor so it is injected properly. In the constructor's parameters, let's add the new parameter private fb : form builder. Now, because we're using Angular Forms and the form group module specifically, we need to import these into our project. At the top of the file, let's add the import. We'll say import, and within curly braces, validators, comma form group, comma form builder from @angular/forms. Okay, we've got these forms modules imported into our component, but we need to go one level up in the hierarchy and also import the Angular Forms module into our app.module module, so it's registered and available for all of the app's components. Let's open up app.module.ts and add the following import to the top of that file. So we'll say import, and within curly braces, reactive forms module, comma, forms module, and then from @angular/forms. Then in the import section of this file, we need to add reactive forms module to the imports array. Great, now we're good with our forms setup. In our template, our button click event trigger fires a function in our backing file named assign wallet address. We need to define this function in our backing file. It doesn't need to do anything earth-shaking at this point, so let's just have it log out a message. So we'll add in assign wallet address. And then in the function body, we'll just console log called assign wallet address. Yes, and that is everything we need to get this new crypto wallet form made with material components. We can save off all of the open files, and we should be able to get a good compile. Let's save this file, the template file, and the component backing file, and see what happens. Great, we've got a successful compile. If you're having issues with your compile, follow the steps we just went through again and look for omissions or fat fingers. Let's go now to the browser and see how this all looks. In the browser, we can see our toolbar and our new form with its single text box. The label is displaying properly, and we can enter text into the text box. If we click the button, we can see in the console that the assign wallet address function is firing. Great, we've got the basic structure and wiring for our crypto wallet completed. Let's go to the next video where we can wire the wallet implementation back to the project's existing blockchain and mining functionality.